Hello and welcome to EELE 101, Introduction to C Programming. And this week we will look at how we will control which instructions a computer will execute. Okay, so the first thing we'll look at are if-else statements. And here you can see a block of code where we have an if, an expression, statement 1, else, and statement 2. The question is, what does this block of code do? Okay, so the first thing we need to know is what is an expression? Because if this expression evaluates as true, then statement 1 will execute. And also notice that we are using these curly braces. Here's the start, here's the end. And if this statement is true, anything between these two braces, okay, will execute. So we can have more than one statement here. But the point is, if the expression is true, statement 1 will execute. If the statement is false, okay, then statement 2 will execute. So if it's false, then statement 2 executes. So here, by setting up the expression, and whether or not the expression evaluates to true or false, we can control which code will run. Okay, so we will next look at what do we mean by an expression and what do we mean by true and false. Also note that this else part, we don't have to include it. You know, we could just delete this out where you'd only have if, expression, and then the statement and then the closing curly braces. And in this case, if the expression turns out to be false, since there is no statement to run, nothing will happen. Okay, so let's look at what do we mean by an expression. Okay, well, there are several things we can put in an expression. And the first thing we'll look at are comparison and relational operators. So if we look at this table, we see a number of comparison and relational operators that we could use. The first one is we could check to see if A is equal to B. Notice that this is different than the assignment. In fact, this is a common mistake, is to put a comparison with a single equal, which is an assignment, and what will actually happen is B will get assigned to A, and it won't be checked where A is compared to B, whether or not they're equal or not. So be aware of that. So if you are trying to compare that they're equal, use two equal signs. Okay, so that's one thing we could check. We could also say, are they not equal? We could see if a number is greater than another one. We could check if variable A is less than variable B, or we could actually see if they're greater than or equal to, so we want the edge conditions to be equal, and in the same manner, less than or equal. So at the bottom here we have example code where we're saying if A is greater than B, that's our comparison operation. If that's true, then statement 1 will execute. Here we don't have an else, so nothing will happen if the statement is false. Alright, so we can also use logical operators. Here we can say if it's not, okay, we can use and we can use or. So here we have a more complicated expression where we're using some relational checks from as last time, but we are combining it with and here. So this statement is saying if A is greater than B, so it's actually a good idea to use parentheses. So here where this is checking, if this is true, and now notice we're using the double ampersands here, okay, and C is less than D. Okay, so now both of these things have to be true for statement 1 to execute. If either one of these are false, then nothing will happen. Right? So we could also use OR where we're using those two vertical lines. Okay. Now, an expression could be just a mathematical expression. Okay, so the question is, what would happen if you came across and just saw this, if that? All right, it's like, huh? You know, how is that true or false? And sometimes you'll actually see this in C code, which is actually not the most readable type of code, but you will see it. And what you have to understand here is whether or not this gets evaluated to 0 or not. Okay, so if it is 0, then it is false. If it's not 0, it's true. So it could be any other number. Okay, it could be -5, it could be a million. That would be evaluated as true, and statement 1 would run. Okay, only when this would turn to 0 would it be considered false. And so the question is sort of why is that? Um, and this has to do with internally in the CPU how checks are done. So it's typically there's a 0 flag. So any um, arithmetic operations that are done, it will say, oh, is the result 0? And if it is, there will be a flag set. And so this is where branching can take place, whether it's branch on 0 or branch on not 0. But the focus is on 0. And since we typically use positive logic, which means a 1 would be true and 0 would be false, we equate false to 0. And then any other thing would be true. And this gets carried up into the C language. Alright, now what if you wanted to make multiple comparisons? Here we have nested if-else statements where we can do if expression 1 is true, otherwise it's false, so then we'll do an additional test if these things are false because we're putting them in the else part, but they could be put in the near statement 1 or the beginning where these are true, but the point is we could be making multiple comparisons. Okay, well there's actually a more efficient way of doing this by using the switch statement. So here we use the keyword switch, we have parentheses, and then you put the variable in that you want to be checked. Okay, and then you have these cases. So if that variable is equal to option 1, whatever you put in for option 1, then this option 1 code, and you can have multiple statements, will run. And then notice that there's a break at each end. So this is what kicks it out of the switch statement when you're done with that particular option. Now notice this only works with integer types, so the variable that you put in here has to be of type, int, okay, because these comparisons need to be exact. So this will not work with floating points, or sometimes if you have a range of numbers to check, okay, it's better to use an if statement for that. Okay. All right, a good way of using a switch statement would be in an option menu. So here would be an example code that you can run where you would say, okay, we're going to print out multiple ways that people say hello in the world. Okay, and you can say enter 1 to print hello in English, enter 2 to print hello in Spanish, enter 3 to print hello in French. Okay, and then you grab that variable. In this case, we are going to put it in the variable option, which is of type int. So notice this is int here. Okay, so now that variable is being checked. So if option is 1, then we print hello. Okay, if option is 2 or 3, then we will print hello in the appropriate language. Okay, other things that we can use to control how statements are run. Here we have what is known as a while loop. Okay, so we have the key word while. Again, we have an expression that is going to be evaluated and determine whether that's true or false. Okay, so in a while loop, everything in the while loop, right, that's between the opening and closing braces here, this will run until the expression becomes false, and then it will stop. Okay, so let's look at this example. Here we have a counter. We're going to initialize the counter to be 0, and then we have a while loop, which is here. Okay, the counter, we are going to see if that's less than 20. Okay, and then we're going to print out counter equals the actual value, and now we're going to increment the counter, and we come back around, and if we started at 0, the next time around it's 1. Oh, yep, that's still less than 20. Come around. Yep, it'll be 2, yes, and so you keep doing this until it's 19, which is true, and then when this one changes at 20, comes around, is 20 less than 20? No, that's false. All right, so we don't execute this, and we exit the while loop. All right, a do while loop is very similar. We still have the loop where everything in here is going to be executed and repeated until the expression here is false. But now notice that the check is at the end. All right, so we will actually do these statements at least once, check whether the expression is true or false, and do this again. So the fundamental difference between a do while loop and a while loop is whether or not these statements are run at least once or not, and whether you want the expression checked at the end or at the beginning. And so here's the similar example here where we have counter, and we're going to essentially do the printf and increment, and then check and do this while the counter is less than 20. Okay, so the fundamental difference is the expression is checked at the end in a do while rather than at the beginning in a while statement. Okay, so here's a for loop, and so this is a very common looping structure where we can control how often the statements are done or executed. Okay, and notice in the for loop there are 3 expressions. We have something called initialize, we have something called test, and we have something called update. Okay, all right. So the initialize part, okay, is where we can initialize variables that we want to have a particular value when we start. Okay, the test is the expression that's tested to see if it's true or false, and if it's false, the looping will stop. And then we have the update, which controls how variables are updated. Okay, so let's look at the for loop here. So here in our initialization, we're setting the integer I to be 0. The test is whether we are checking to see if I is less than 20, and the update is I++, or increment I by 1. Okay, so here we have a single statement, print count equals, and we'll print out the current value. Notice we are going to start with I equals 0. We are going to do the test to see, is it less than 20? Okay, it is, so we're going to run the statement. Okay, and then notice at the very end is where this update is going to occur, and we're going to come around and test it again. Okay, is it less than 20? Do the statements here, increment or do the updates, and come around and test again. Alright, so kind of as a comparison how a do while loop could function as a for loop. Here we have the initialization here. If you did a do while, you would actually have to put the initialization before you entered the loop. Okay, you have the statements that you want repeated. Okay, here you would have to do the update inside the loop and do the test at the end. And so it would be a similar construct. Okay. One other thing we should point out is the use of a comma operator. You can put commas in both the initialization and update fields. So here's an example where we will actually have 2 variables that are initialized. Here where it will set I equal to 0, and we could set x equals to 10. So we could have as many expressions as we want in here as long as they're separated by commas. So we could have 10 here. Here we have the single expression that's going to be tested, whether it's true or false, and if it's false, the looping stops. And then here we have the update. Notice again that we can have multiple updates, each separated by a comma. And here, notice we have sort of a shorthand, which is called a compound assignment operator. Here we're going to take I, add 2 to it, and so this is where we're saying plus equal is the same thing as writing I equals I plus 2. We can write the shorthand as just saying I plus equals 2. So this is a C shorthand. We can do the same thing for multiplication, where here we would be multiplying x by 3. Instead of x equals x times 3, we can just write it as x times equals 3. Alright, so here you can make a for function like a while loop. The main point here that I just want to show or point out is sometimes you'll see this for loop with empty fields. You'll just see the 2 semicolons. Okay, and what you should recognize here is this will be an infinite loop. This thing will just run forever. Okay, and sometimes this is done on purpose in embedded systems, because when you're writing multi-threaded tasks in a real-time operating system, these tasks are understood just to be running forever, and this is how you would set them up. Okay, so let's make use of our looping constructions and some testing. So we will plot the function x cubed minus 6x squared plus 4x plus 12, and we're actually going to plot this in CH. Okay, so here's the function that will plot this, and we'll go through what all this code means. Okay, so let's start out here. Alright, so the 2 libraries that we are including, okay, we're using the math library, math.h, okay, because we need this power function, because we are using exponents, so we want to have the ability to take a variable and raise it to a particular power, okay, because we have x cubed, we have x squared, okay. And since we're plotting it and we're going to make use of CH's plotting routines, we need the header file for that one as well. Okay, so that's just because we're using functions that have already been written for us. Alright, the next thing we will use are some define statements. Okay, the reason we're going to use these is because we don't want to, put 800, let's say we're going to plot 800 points here. In our code, we don't want to put a bunch of places where we have 800 and then later on go, oh, I would really like 1,000 points. Okay, and now you have to find all the places in your code where you wrote 800s. We would like to have just one place where the 800 is, so if we change it, we only change it once. Okay, so what we're making use of here is the compiler's preprocessor which is this define statement. So in our code, we will use endpoints, okay? And what the compiler does on the first pass is wherever there's endpoints, it does a replacement here with 800. So if we change it 1,000, we only have to change it here, and then the compiler does the job of replacing all those locations for us automatically. Okay, so here we can control how many points we're going to plot. Here, since we have y equals x cubed, the function, well, what value of x are we going to start plotting? Here we're going to start at -2, and then we're going to increment x, and what's our increment size? Okay, and that's what our step size here. And so if we want to change it, we just change it here, and we don't have to go searching through our code to find that location. Notice that there's no semicolon here at the ends, at the end of the define statements. Um, so every statement has to have a semicolon to end with, yeah, but not with defined statements. All right, so here we have our main, which is the starting point of our program. And the first thing we're going to do is declare all the variables that we need. Okay, so we have int I, so we're going to use that as an index into our arrays. We have x, which is going to store the current x value. And then we need to actually store the x and y values, which we're going to use later in plotting. And we need a data type for CH of all the data structures that need to be allocated. Okay. Notice here that we put endpoints because if we change it to 1,000 points, we need the array to be 1,000 points. Okay. So we have to allocate as much memory to store the points that we will be creating. Alright, so here's our for loop, and so this is actually where we generate all the values, okay, and we are going to use a compound initialization here. Notice we've got the comma here. We are going to start with our index I equals 0 because our arrays start at 0, so that's where we want to index the position in the array, and we are going to start with x equals start, and notice at the top we had defined x start to be -2, so at the first pass the compiler will replace this statement with x equals -2, and if we want to change it, we just change it up at the beginning at the define statement. Alright, so in this case I is going to start at 0, x is going to start at -2, okay, and that's the initialization. Alright, now we need to set up the test. Okay, and here we are going to run it n point time. So I is going to be incremented, and every time it's incremented, it's going to be incremented by 1. And so this will run until I equals endpoints, and that's false, and the looping stops. Alright, so the update. Okay, so here we are incrementing I. So we're using that both in the test and the location of where we're sticking our values in the array. Okay, so I will be 0, then I will be 1, then I will be 2, and we will be putting in the appropriate values. This is where we're controlling how x is changing. So x starts at -2, and then the next time we're going to add x step size, which is 0.01. Okay, and every time this loops, we are incrementing x a little bit. Alright, and so now the actual functionality or the statements that we're executing here is we have this x array, so we want to keep track of what x is each time, so we put that in our x array. And now notice we compute the polynomial, so this is x cubed. We're using the power function where x raised to the third power. Okay, here we have -6 times x raised to the second power plus 4 times x plus 12. This will get evaluated, and then that result gets put into the y array. And we'll repeat this endpoint times, which in this case is 800 times. Alright, so when we're done with this for loop, okay, once we've generated all 800 points, okay, next what we're going to do is actually plot it. Alright, so here we're using CH plotting routines. Notice we have a data structure written for us, so we're saying plot, we have the period, and then we can use the functions that's part of this data structure. So here we have math coordinate. This is a function call that sets up all the plotting coordinates for us. So it's just something that we have to call first. Okay. Next we can say plot.title. In the double quotes we can have whatever title we want showing up on the plot. We can label our x-axis and y-axis with what labels we want, and here we're just saying they're x and y. All right, and now this is where we plot it. So we have plot data to, well, this is data 2D curve. Okay, so it's two-dimensional data. We are putting in our x values, so this is the array of x values. We're putting in the array of y values, and we have to tell it how many points are in those arrays. In this case, it's 800 points. So notice there's a lot of places in our code where we were putting endpoints, or if we were hard coding it, it would be 800, and then if we decided 1,000, there would be a bunch of places we'd have to go find. It's likely we would miss one, and then we would have something wrong in our code. And then we have to actually call the function that will do the actual plotting. And this will plot our function, which is here. All right, so now the question that we are going to ask is, in this particular range, what are the maximum and minimum values that occur between -1 and 5? And at what x values, here, what x values do these occur? Okay. Well, let's have our program find those for us. Okay. So there's a couple new libraries, functions we'll need, so we need to include libraries. So here we have the appropriate header files for those libraries, standard I/O for the printf function, and we have a float.h because these are some defined statements that we will make use. For example, the double max is the largest value a double can be. We are also going to add some double variables, x min-max and y min-max, for storing those particular values. Okay, all right, okay. Our for loop is the same because we're just generating the same points again. All right, but once we're done generating the points, we now need to go through and find the maximum and minimum places. Okay, all right. So here we are going to set x min and x max to be -1. From our plot we've seen, we know that those won't be at -1 at the end. And here we're setting y min to be double max, which is actually the biggest possible value. So we know it's going to be smaller than that. So if we're down below when we're searching for the minimum, we're going to replace it and check it. So we always want to start it at the biggest possible value. And our max, we want to start at the most negative value we can start as well. All right, so now we're going to do the for loop. So we're going to go through all the values again, okay? And we get the current value, so we're going to go through, I is going to go from 0 to 799. So this is going to repeat 800 times. So for each time, we're going to take the current value of x. And now what we actually want to do is check to see if x is between -1 and 5, because we actually plotted it. We started from -2 and it went probably to 6 or so. So we're actually wanting to only check within a certain range. So here we have a if statement, right? That if true is going to run all this code, and we're going to check, is x greater than or equal to -1? So we want that to be true. We also want x to be less than or equal to 5. We want both of these to be true, so we have to use the logical AND. So if this entire expression is true, meaning x is between -1 and 5, then this code runs. Okay. So now we want to start checking to see if we have the max values for y and the associated min values. So we're going to do these separately. So associated with each value of x is also the array y, and so now what we're going to check is the current value of y less than y min, right? Now notice we started with y min to be the maximum value possible, so of course the first time through here this will be less than y min. So if the current value is less than what we've kept track of, well, we need to update our y min. So if this is true, meaning it's less than, well, that's the new y min. So we need to set it to the current value that we're checking in the array. And if that's true, we also want to keep track of what x was at that location as well. Okay. So this runs, and each time if something is less than the current y min, we are going to replace it and keep track of it. Now here we do the same thing with y max. It is currently the most negative, and we're saying is our current value of y bigger than that? If it is, that is the new y max, and we also keep track of where the current value of x associated with that y. We need to save that as well. So this goes through the entire array, checking it, and at the end we will have found the minimum and maximum points. That will be stored in y min, x min, that's the coordinate pair for that point, and y max and x max is the coordinate pair for that point. Okay, and now here, when we're done, we'll just print out saying the maximum of y occurred at this location, and do that for both the y min and y max. Alright, well, we also want to actually plot this on our plot, so we can actually use those coordinate pairs as a point. And so here, instead of doing a line type, here we're actually changing the type, and we're changing the color for the previous line to be red. Here we have a point, and we can control what the point is. So here we are associated, this is the data set. So notice the first data set, 0 is associated with all the line information, 1 is associated with the first point, 2 is associated with the second point. Okay, 3 is the type of point that we want, so it's like the symbol, whether it's a star, point, X. Okay, the third value is the size, how big of a symbol do we want plotted, and then finally the color. Okay, so here what we're doing is, in addition to the line data, we are plotting 2 points, and this is how it shows up. So the max is being plotted in a blue star, and the min is plotted in the green star. Now notice, you could say, well, this is actually not the minimum of the function, because there's a minimum over here and max here. But remember, we restricted our search to be within this range here, okay, between -1 and 5. Alright, so now you are going to have to do this for your programming assignment. Okay, so last time we looked at a voltage divider where we could compute the voltage across a resistor. Alright, so we are going to rearrange this a little bit. So now we can model a battery which has a voltage source and some internal resistance. Okay, and now we're going to have a load resistor, and the question that we want to find out is, what is the power going across this load resistance? Alright, okay, so now power is just current times voltage. Okay, and so we have power times power across that resistor is the current flowing through it, which in this case is I load, and this is all the same current, so it's the same current we had before, which is the source voltage divided by the total resistance. Okay, and now we're going to multiply it by the voltage across that. Well, from Ohm's law, we know voltage is just current times resistance. Oh, we have two current terms here, so this power is just the current squared times the resistance value. Okay, now let's modify this a little bit. So instead of having two independent variables, our source and our load, let's just make our load equal to be a constant times the our source. Okay, and C is some constant or real number. Okay, so let's redo this now, where our load is now C times our source. So we now get this final equation where we just have the voltage source, the resistance source, and a constant value. Now, what you need to find out is, well, first of all, you will need to plot the load, P load, as a function of this constant value C. Okay, so in a sense, you will, just like we did for that polynomial, so instead of x, this will be different values of C, and instead of y, this will be P load. And so now you'll get some function that you will plot. Okay, and then what you need to find is, is there a maximum value in this plot? And if there is, what is the value of C when this maximum of P load occurs? Okay, all right, so here's your programming assignment. So you will need to write a program that numerically solves the maximum power transfer problem. Okay, so you will need to ask the user for the source voltage and the source resistance. Okay, that will come in as a string character array. You need to convert these to double types. Okay, and also confirm um, the values that were entered to the user. Okay, all right. Now, just like which was done for that polynomial, you need to create um, an array that will store all the C values. Okay, so you need to generate C values over the domain, or between the values of 0 and 10. Okay, now the number of points you put in the array and the step sizes between them are up to you. Okay, so use a define statement that we did before, like endpoints was 800. Okay, so you can easily change the number of points that you're plotting. Okay, then you'll need to calculate the power P across the load resistance for a particular value of C. Okay, so now you're going to have these coordinate pairs of C versus power, and you're going to generate 1,000 of them between, or that the number of points is up to you, but between 0 and 10. Okay, you're going to store the power in an array called PA. Okay, the values of C are going to be stored in an array called CA. Okay, notice that these arrays are going to have the same number of elements. Okay, and just like we did in the polynomial, you will need to go through the P array, find that when does the maxima occur, and what is the associated C value when this occurs. Okay, and ultimately what we're going to ask you is, what is the relationship between the load resistance and source resistance when this maximum power transfer occurs? Yeah, what is that C value? Okay, all right. So this is almost identical to that polynomial plotting function and searching for the min and max, except the actual function you compute the load will be different. Okay, but the structure of the program is pretty much the same. Okay, and this is the final question that we are after. What is the relationship between our load and our source when maximum power transfer occurs? And this is known as the maximum power transfer for this circuit. So that's what you need to do, and good luck programming.